Welcome to Fish University, your one-stop shop for the science behind fish management. It is part of the Natural Resources University Podcast Network. I'm Wes Neal, your host. I'm an extension professor of fisheries and a researcher for Mississippi State University. Join me as I talk to researchers, managers, and landowners about the tools and science and the tricks of the trade for managing fish, water, and habitat. The goal is for you to have better fishing and a healthier aquatic ecosystem. So grab a notebook and the beverage of your choice and relax and enjoy Fish University. Welcome everyone to Fish University. I'm glad to have everyone here today. One of the things we're going to talk about today is we're going to be talking about fish habitat. And a lot of times when we think about fish habitat, we're thinking about structural habitat, physical habitat, things like trees and rock piles and creek bottoms and points and humps and so forth, things that we can see and touch and target when we're angling. However, there's another side we oftentimes don't think about, and that's the water quality side of habitat. And there's a lot of things that go into water quality, and we could spend many episodes talking about all of them. Today, I'm really excited. I've got our Extension Associate Professor, Dr. Beth Baker, who is a specialist with nutrients and sediment. Beth, I'm so glad to have you here.
Yeah, it's great to be here. Thank you for the invitation.
So, Beth, tell my audience a little bit about how you got into the field of water quality and what brought you to Mississippi.
Sure, absolutely. It definitely wasn't a planned route, and it wasn't a straight line. So I actually did my undergraduate in pre-med, right? I thought I was going to go the medical track, and I started doing research to prepare for that. And the research I started doing was in aquatic toxicology. And so I was working in a lab that really was actually surveying fish and the effects of different contaminants in the environment on fish. And that really just changed my perspective about what health is and how our genetics are part of that, but the environment is a huge part of that too. And so that just kind of changed my trajectory. I stayed at St. Cloud State University, which is where I did my undergraduate as well. I stayed on with the professor I was working with to do a master's in aquatic toxicology. And so after finishing that program, I really wasn't entirely sure if I wanted to do a PhD, but I was enjoying the work I was doing at that time. And just kind of serendipitously met a professor here at Mississippi State University who was looking for a PhD student at the time, and kind of made a jump at that point, coming to Mississippi State University to really switch the focus of my research from that aquatic toxicology to nutrient transport from agricultural systems to our water bodies and ultimately to the Gulf of Mexico. And so after completing my PhD work here at Mississippi State University, I was lucky enough to stay on as a professor. And somehow I'm going on year 12 this year here, but of course, really enjoying the work that I do.
Well, we're glad to have you here. One of the things that you do as an extension professor is you coordinate a number of programs, honestly, but two programs in particular that are appropriate to what we're talking about today, and that is the REACH program and the Water Stewards program. Can you tell us about those programs?
Yeah, I'd love to. The REACH program stands for Research and Education to Advance Conservation and Habitat. And really all of that work has been centered around monitoring and documenting the benefits of conservation to protect soil and water resources. And so the research side of that definitely focuses on nutrient transport and those conservation practices, but the education side is also a huge part of our programs. And so that's education for stakeholders on the ground, like landowners, land managers, producers, and continuing education for agriculture and natural resource professionals as well, all in areas of this natural resource protection, some of the threats to our sustainability, and understanding the evolving science around best management practices to protect and conserve our resources. And so you're right that there is a number of what I would call sub-programs that we've developed under this REACH umbrella to target all these different audiences and all the different scales in which we can try to tackle soil and water protection. One of those being the Water Stewards program. And I could talk to you for several episodes just about the Water Stewards Program. So I'll try to share it in a nutshell, just for the sake of time. But this is really, it's a citizen water monitoring program. And it's tailored around three primary pillars where we educate citizens about water resources, particularly those in Mississippi. And then we train them in EPA-approved methods for water quality monitoring. All of that combines to help us build capacity in our local communities for folks to identify and protect their water resources at a local scale. And one of the primary drivers for the REACH program, Water Stewards, and all of our sub-programs is that need to reduce and prevent non-point source pollution from landscapes and to protect the state's water resources. So it's really exciting to get to work across so many avenues towards this larger goal.
So Beth, you said a couple of terms there we probably should define, the first of which is non-point pollution. Really, when we're talking about non-point pollution, you mean, it's not coming out of a pipe from a factory. It's something that we're spreading across the landscape, like fertilizer in an agricultural setting, sediment coming off of farm fields, something that's sort of a diffuse source. Is that correct?
Yes, definitely. We're talking about some sort of pollution that doesn't really have an identifiable origin. And then you'd really think of it as anything moving over the landscape, like you mentioned, from a diffuse source. And so that could be something, as you mentioned, in an agriculture landscape that we're applying to the land. It could be a result of just land use in terms of disturbing soil, whether it's for agriculture or construction or development or whatnot. And then in some cases, it can be other things that we apply to the landscape in our urban settings as well.
Yes, certainly. Everything from runoff from our highway system. If you're up north, it's not uncommon to see a layer of salt within natural lakes that's come from road salt that's used during the winter for ice. And people don't think about those things running off the landscape and into our waters, where they have significant impact on the ecosystem, and the fish are affected by that. So that's why we thought it was a good idea today to have Dr. Baker here and talk about two particular types of non-point pollutants, sediment and nutrients. And I think maybe we should define what we mean by sediment and nutrients before we really get too in depth.
When we're talking about nutrients, we're really talking about two specific nutrients that we somewhat generalize by saying nutrient pollution. But typically, our non-point source pollution is characterized by a few specific pollutants that we end up identifying in the environment. So the two nutrients are going to be nitrogen and phosphorus. And nitrogen and phosphorus both are two primary plant nutrients. They're two nutrients that all life need. They are involved in various components of living organisms. And so they're a good thing. We need them. And yet when we have them in excess in environments in specific forms, they can help things grow at a rapid rate that our food webs are not necessarily prepared for.
Yeah, and the sources of these from a human standpoint would be when we fertilize a farm field. Say we're fertilizing soybeans. A lot of times they're spreading a nitrogen or a high nitrogen fertilizer. The phosphorus, sometimes the fertilizer contains phosphorus, but it comes from other sources we don't think about. Like a lot of the detergents back in the last century were phosphorus-based detergents, and those detergents, we'd wash our clothes, the water would carry the detergent down the drain and it would end up in our waterways. And we were basically adding phosphorus to our waterways without even knowing about it. And it had a lot of bad consequences. You mentioned that with the nutrients come plant growth. Well, plant growth is a good thing for all ecosystems, obviously. In farm ponds, for example, we oftentimes manage by fertilizing. However, you don't want to over-fertilize because too much plant growth can cause major problems. And one thing I think people don't realize is the relationship of plants to dissolved oxygen in water. Everybody thinks, oh, plants create oxygen and animals use oxygen. Well, that's not entirely true. Plants create oxygen and plants use oxygen. Plants are always using oxygen. Anything that's alive is using oxygen. During the daytime, when they're photosynthesizing, they're producing more oxygen than they're using. But at nighttime, when they're not photosynthesizing, they're using oxygen but not producing it. So you end up having a cyclical fluctuation in oxygen levels throughout a 24-hour period. So if you have a farm pond, or if you have your local lake or your stream, if you don't have a source of oxygen coming from an aerator or from turbulence within the stream, then what you typically expect to see is that oxygen levels will peak sometime mid-afternoon when photosynthesis is at its highest, and then they'll go down, and at really late at night, usually right before first light, oxygen levels will be at their lowest. And this is, if anyone here who's listening has ever worked on an aquaculture farm, they know that you have to drive out at 5 a.m. with the oxygen meter and check the ponds, because that's when they're going to be low. That's when you're going to need to turn the aerators on to save your fish. So plants do produce oxygen, but plants also use oxygen. So when you have too many of them, you can have an oxygen depression or an oxygen crash. So we've been talking about nutrients, Beth. Let's talk about sediment a little bit, because a lot of times people don't think about sediment in the water.
Sure. Sediment is really just the soil moving and the particles associated with the landscape and our natural landscapes when they are moved from them. So another way we can refer to sediment being in our waterways is erosion, and which is a natural process. So just like nitrogen and phosphorus are natural elements to find in our water bodies and in our aquatic systems, sediment's another thing that is natural to find in our water bodies. Erosion's a natural process. But the reason it's also a non-point source pollutant is because our land use activities can exacerbate that rate of erosion. And so then we have more soil loss from the landscape, whether, again, it's an agricultural field or a construction site, or even, just from losing the natural elements of our water bodies, like riparian areas. Maybe we'll talk about that later, but the vegetation around our water bodies, we can have increased erosion from even inside our aquatic systems, right? The inside stream banks of rivers and streams and whatnot. So I always like to make the point that these are natural processes, but our land use activities really increase the amount of nutrients or the amount of sediment that we find in our aquatic systems.
You made a very important point that the terrestrial vegetation helps hold these sediments in place on the landscape. And when we remove the vegetation, let's say construction site for a new apartment complex, it's not uncommon to see the local stream, the local pond turn whatever color the soil is, because all of that stuff tends to wash away. I think in one of my episodes I discussed the Mississippi escarpment area, the Mississippi River, and how a lot of that was just sediment from up north that blew in millions of years ago, and it was perfectly stable for millions of years, and then agriculture came in, cleared the trees, and suddenly tremendous amounts of erosion began to occur. So that's how sediment gets into our waterways. Now, sediment is just really, you say it's soil, so it's basically particulate rock and organic matter. That carries with it nutrients and minerals as well.
Yes. And of course, it can change the clarity or the turbidity of the water, which can really change how much heat water holds and therefore how much dissolved oxygen it holds. So none of these things are really disconnected in our aquatic systems or our terrestrial systems. Everything's a little bit interconnected. And so understanding how each pollutant works with the environment, both impacts and is impacted by, I think is really important to note too, especially when you're talking about pond water quality and habitat for fish.
Yeah, and the turbidity, you mentioned it can change the temperature of the water, which is very important, but turbidity also will shade out the photosynthesis. It will block the sunlight from penetrating the water. It'll absorb the sunlight, causing the heat, but it prevents the sunlight from making it to the aquatic plants or the phytoplankton that would be the base of the food chain. So you can end up with a very turbid waterway, whether it's a pond or a river or a lake. It affects the productivity of that system in a way that, if it persists for a long time, could really reduce the productivity. And the productivity is important because, as we all know, the basic food chain of a small body of water is you have the phytoplankton, which are the small, tiny, microscopic plants. They feed the zooplankton, which is the small, tiny, microscopic animals. And then those are eaten by insects or small fish and eventually by big fish. When the plankton levels drop, the amount of energy going up the food chain, the bass, for example, or the larger fish, And those fish then either starve or population sizes decline. So having muddy water is not a good thing under most circumstances for sure. So we've established that nutrients and sediment are both natural, normal, and necessary in moderation. But in excess, they're problematic. Let's talk a little bit about some of the things that can happen when we have too much of a good thing.
Sure. That's a great question. So in the case of nutrients, and I'm going to zoom out a little bit because a lot of, the work that we do is focused around preventing nutrient pollution into the Mississippi River Basin and the Gulf of Mexico. That is because there is an annual hypoxic zone in the Gulf of Mexico that threatens the fisheries there and the environment and ecosystem services of the Gulf of Mexico. So we have to ask the question, why does that occur? And one of the drivers of that hypoxic zone, and I'll just define that in saying it's a zone of low to no oxygen, which again, an hypoxic zone can occur naturally. The one that occurs in the Gulf of Mexico on an annual basis has some drivers that we can identify and the scientific literature has identified. Some of that is just the amount of nutrients transported down the Mississippi River Basin, which is home to the breadbasket of the Midwest, where we have a lot of agriculture production. Here, of course, in the Mississippi Alluvial Valley, we also have a good bit of agriculture production. And there's also a number of cities right along the Mississippi River and its tributaries that might discharge wastewater into it as well, after it's been cleaned, but carrying some nutrients with it as well. So all of that discharge moves down to the coastal areas, into the Gulf of Mexico. And along with other drivers like rainfall causing higher levels of discharge, those nutrients end up in the Gulf of Mexico each year. And if the conditions are optimal, then they drive algal blooms. And the algal blooms themselves aren't necessarily a huge issue, but when that algae die and they're decomposed, that process sucks oxygen out of the water column. And then you start having issues for any of the species that live there that require some oxygen to survive, and you have this area of low oxygen. So that's really the concern, and you kind of have to understand how each domino falls to really get to both the root causes and understand the big picture there. And I still, even at that level, somewhat simplified the whole issue of how the nutrients really move from some local area down to the Gulf of Mexico. And so you can actually have similar issues like that, even at a local scale. It doesn't always have to be the nutrients travel down the whole river basin into the Gulf of Mexico, and then we have this hypoxic zone in a coastal area. You can have high levels of nutrients and low levels of dissolved oxygen after algae grow and die, and the decomposition sucks that oxygen out of the water, even in our local freshwater areas too.
In 2021, the area of the hypoxic zone in the Gulf of Mexico was 6,000 square miles. That's 6,000 square miles that oxygen levels were depleted to a point where marine life struggled to survive. That's a pretty significant amount, especially when you're talking about all the industry, the oyster industry, and other fisheries that exist in that area. This is a substantial situation, not only for the environment, but for the economy as well in these regions. You also mentioned that it can happen at the local scale, and when you have too many nutrients going into a pond, that the pond will turn pea soup green, and you run a risk of an oxygen depletion. My master's program was working in farm ponds, and I lost 3 of my 4 ponds to fish kills during the 2.5-year period I was working on my master's degree. One of them, we had cattle feedlot upstream of the pond with a sedimentation pond to sort of catch the cattle waste. We had a big storm, blew out the levee for that, and it all flowed into my pond. So now you have a very small body of water, maybe a quarter of an acre, flowing into a large body of water, maybe 16 acres. But that water was carrying such a heavy load of organic matter, basically cow poop coming in with all the phosphorus and nitrogen that it contained, and organic matter, that the organic matter was a source for biological decomposition, which bacteria, when they break up organic matter, they use up oxygen as well. We had a major fish kill, and everything died. Beth, I know you've worked at even the smallest levels. I know you've done a lot of work in like agricultural ditches and canals, right?
Yeah, we've been, I guess maybe that's one of the experiences that really helped me just have a little more perspective on the complexities of nutrient management and nutrient pollution, is having worked at a pretty small scale and measuring nutrients in water bodies that are right adjacent to farmlands, and doing lab analyses that really measure very small amounts of nutrients, and then also getting a chance to work with stakeholders across the whole Mississippi River Basin and studying biogeochemistry at a global scale. Because the nutrients that we move and put on our landscapes come from somewhere, right? They are found in different areas of the world. When, in the case of nitrogen, we typically synthesize it from nitrogen in the atmosphere and then put it in a biologically available form for plants. So we're moving it, around the global landscape. And then when it comes to phosphorus, phosphorus is typically found in specific ground reservoirs of mineral deposits of phosphorus. And we're moving that at a global scale. So we have this really large movement of biogeochemistry, and to just know it at a global scale and then work at a local scale, then you really get to see that if we want to find long-term solutions to this, our landowners and our citizens can do a host of things, but long-term solutions are going to take a little more planning and long-term change.
Certainly, at some level, I feel like we're putting a lot of the blame on agriculture, but the reality is it's not just agriculture, it's everything we do. I mean, many of the problems that I deal with in small homeowners association lakes and small ponds is usually the local homeowner inappropriately applying fertilizer to their lawn and then having it wash into the lake. I mean, if you read how to properly apply the fertilizer, it will tell you when to apply it, when not to apply it, how much to apply, don't over apply, because what happens is you put too much out, or you put it out right before the big rainstorm, and it just moves downstream. It's meant to make your grass grow, but it's making either aquatic weeds or plankton grow in a location you never intended. So all of us need to be thinking about how we use nutrients in our daily lives so that we try to reduce their downstream movement.
Yeah, and I'll just add to that, because I definitely, even though we talk about agriculture being a source of the nutrients, it's far more complex than to just say that is the reason, because the exact mechanism of it moving from a field to a downstream water system is really the driver of rainfall. That's the physical force. So you can't say that necessarily just because we put it on the landscape. I first of all, wouldn't use the word blame in any of these conversations, but it's so important to really understand the root drivers. When it comes to food production, we all, as a global community, are the recipient of that and buy food left and right. And our food security, food, fiber, fuel, or whatever you want to call it, because the crops we grow really go to multiple different uses, not just food. But we have the highest global population that we've ever had, and it continues to grow. And so just the sheer scale of producing that much food changes how much nutrients we move at global scale. So then it's even harder to say, even if we did the best nutrient management, we might still have a really large rain event at the wrong time that still moves and transports nutrients into our aquatic systems. And so just the amount of global change that we're experiencing drive a lot of these mechanisms on the ground, and it's really too complex to simplify, which is why we have to hit it from all angles.
Yes, certainly. And we've sort of hit on the concept that too many nutrients can lead to oxygen problems, but there are a lot of other fairly serious issues that can arise from nutrient enrichment. For example, everyone's probably heard of red tides in Florida and in the Gulf of Mexico. Those are a dinoflagellate that thrive on nutrients. And when nutrients are high and abundant and conditions are just right in terms of water temperature and other factors, these things can explode into what we call a bloom. And a bloom is simply just a big population explosion. And when they do, they're capable of releasing certain biological toxins into the water that affect everything. I mean, we've seen sea turtles and dolphins and all fish die, but they affect people, they affect land animals. People get sick, they aerosolize, they enter the air, and then they can move away from the water, and people can inhale them and have symptoms from the toxins as well. And then we have the other thing that is more common in freshwater but can occur in saltwater and marine environments, and that's the cyanotoxins, the cyanobacteria. Beth, I know you probably have to deal a fair amount with cyanobacteria. I do too. I get a couple calls a year about people's dogs dying when they went swimming in their pond. Sometimes it's a cyanotoxin that's caused it. The dog goes swimming and gets out of the water perfectly happy and healthy, licks its fur, goes inside, and 12 hours later it's in pain and dying. Cyanobacteria and red tides or dinoflagellates, they're all part of the normal cycle of phytoplankton that exists in all bodies of water. However, they're exacerbated when nutrients are in excess. So all of these things are good reasons to try to do our part in keeping nutrients at a minimal in our waterways. So I know you've spent a lot of time with your programs working on how to do that and what are some of the best management practices to try to reduce nutrient enrichment. Let's talk about that.
Absolutely. There's several kind of layers to the best management practices. So I'm going to hypothetically start as if we were in a field, putting a fertilizer onto a field. And as you mentioned, there are smart handling practices to do that. So that's kind of step one at the source when nutrients are being put on the landscape. So we would refer to that as nutrient management. And because we're working in a farm field in this scenario, it would also include soil management. So the goal of nutrient management is to optimize the efficiency, to make sure that the nutrient that we want to grow the plant for its intended use gets to the plant and not downstream. The strategy there is called 4Rs. And so it's using fertilizers at the right rate, using the right source, putting them in the right place, and putting them on at the right time, just to reduce runoff risk and really optimize nutrients getting to the plant. So the other element of that is just, and of course you could take the same best management practice approach there in handling to urban areas, lawns, gardens, golf courses, whatever area you're applying these. But the next one, in tandem there is also smart soil management. So the more we disturb soil in any system, the more opportunity we have for soil loss because it's disturbed. It loses its aggregate stability, which is a technical term, but when it can hold that aggregate form, it just means that the particles are glued together better and it can resist forces like wind and water, which are the primary drivers of erosion, along with chemical erosion, but we'll stick with wind and water. So smart soil management, reducing soil disturbance are kind of those in-field practices, things that you would do right at the primary source. And then this next level of management happens really at the landscape edge of field, is what we call it. So where the water is being drained or is draining from a landscape, whether it's through a culvert or an overland flow or in a ditch to another water body. And we've got a few tools in our toolbox here for management at this scale, but the main ideas are going to be around retention and removal. So this physical water retention or slowing water flow, which isn't always a feasible goal. And I'll give you an example of that, at least from an agricultural system. We get a lot of rainfall here in Mississippi. So even though we want to slow water drainage during the growing season, if we get a 4 to 6 inch rain that runs a risk of crop damage, we don't want at that point to retain any water on the landscape. We need to get it off as fast as we can. And in most agricultural systems, many agricultural systems where you get a fair amount of rainfall, drainage is one of the key elements to having a strong and resilient and healthy crop at the end of the year. So it's kind of a balancing game when it comes to drainage, which is why I think it's at least worthy of mentioning, because in the grand scheme of things, we need food and water, right? So we really need to balance our goals when it comes to making management decisions. So sometimes retention is going to be an optimal strategy, and sometimes it's not. But going back to these edge of field practices, in theory, we're aiming for some retention and removal of both sediment and nutrients. So if we want to physically, slow down water flow, we might use weirs, which are small check dams. They kind of slow water flow, even creating mini wetland type habitats in some scenarios, or any other water holding structures, perhaps a sediment basin. So like a pond that's there to capture sediment. Storage ponds could be another example of this. Treatment wetlands. and even vegetation. Like this is one of our main tools. So in some cropping seasons, you grow a cash crop during the growing season, and then you might not grow anything during a fallow season. Where in Minnesota, where I'm from, that's not feasible because there's snow cover. But here in Mississippi, we don't have snow cover and the ground's not frozen. So during that fallow season, we might grow a cover crop to add vegetation to the field to take up residual nutrients and add some more armoring to the soil to reduce sediment transport. Those are some ways that we can add tools at the edge of field, in field for taking up nutrients and slowing that water flow and giving us a little more opportunity to really keep nutrients at the local level, right? Because that's the goal. If we have them in the landscape cycling a little more efficiently, they're going to be there and not in a downstream water system. So that's what we're aiming for. And then there's another level of this, which I mentioned at the beginning of the podcast, but it comes back into play when we're designing nutrient retention on a landscape. And that's having intact habitat features, because we've lost so much riparian cover just around stream corridors, natural wetland areas, any of these transitional zones, we call them in ecology, where there's a lot of biodiversity in species and plants, and they're natural areas of water storage. So they have dual function here, especially now, which is why we'll probably hear more and more about riparian areas and wetlands and transitional landscapes. For one, because we lost so many. Two, for flood mitigation. So when we see these events of like frequent flooding, flash flooding, where do we store the water? Well, in these landscapes that naturally store water is a good idea. So they have that benefit of water storage. In some cases, the root systems of trees in riparian areas can enhance water infiltration into groundwater storage. The canopy cover for our water bodies is really beneficial for moderating temperature because it provides shade for some of our water bodies, like small streams where the canopy is close enough to fully cover the water body. And then all of that vegetation provides stability for the soil, the stream bank, and because they're plants, they take up nutrients. There's so many just benefits to those areas. So any places we can add grass buffers around fields, golf courses, even in urban areas. I mean, we go so much from concrete to culvert and then shoot it out in a water body that wherever we can have some interception in our natural spaces, that kind of natural engineering is probably going to become kind of a gold standard for us here in the future.
Yeah, I love the fact that you said wetlands. I don't know how many times. If memory serves, I believe that we've lost a little over half of the wetlands in the United States in the last few hundred years. Wetlands are so important from a standpoint that they slow down the water. They allow the sediment to fall out. They take up the nutrients. And you mentioned a lot of that with the vegetation. The other thing vegetation does that people don't think about is vegetation cycles the water back to the atmosphere. The roots take up the water flows up the tree and out the leaves. And without that, or with the example you gave of asphalt and parking lots, the water doesn't go in the ground. The water doesn't evaporate. The water runs straight off immediately and carries everything that's dissolved on that parking lot with it. That's one of the reasons we have these problems now of increasing flashiness of our streams, more flooding, but also all the nutrient runoff and sediment problems that we have is because we've changed the landscape and all the services it provides.
Yeah, I appreciate that kind of whole summary of the wetlands and bringing back in all of those benefits, because when we talk about reducing nutrient pollution, there's still a lot of discussion about how much we need to reduce it by, and we largely lack some numeric nutrient criteria on the regulatory side. That's because it's really difficult to identify what's the right level. Like, we know we need to reduce it, but how much? And it's hard to say that if we don't have an intact ecosystem to cycle the nutrients into our aquatic and terrestrial food webs. And so the idea of reducing pollution needs to come hand in hand with restoring our natural habitats and that natural cycle of nutrients.
Hello, everyone. Thanks for listening to Fish University. Do you have a question or a topic for the podcast? If so, you can email me at Wes, that's W-E-S, .Neal, that's N-E-A-L, at Mississippi State, that's M-S-S-T-A-T-E, .edu. Or instead, please visit the Fish University Facebook page. On the Facebook page, you will find useful articles, videos, stories, and other information, as well as updates on upcoming podcasts. Not to mention, you can send me a private message with questions or suggestions. Just search Fish University and look for our colorful logo. And please follow the Fish University page. We need your support. Now back to the show. So Beth, you've been talking about some of the best practices that we as a society need to do, but the individual landowner, what can the individual landowner do to make a difference?
Yeah, that's a great question, because we've talked about kind of how large these issues are at a regional scale, but everything that we need in terms of solutions happens at a local level, whether it's identifying an issue in the first place or restoring, habitat components or implementing best practices. That actually all happens at a very local level. So, we could tie it back to water stewards and the work that citizens can do, whether it's monitoring, and it doesn't always have to be with a chemistry kit or by measuring dissolved oxygen or tracking bacteria in a water body. Some of the indicators, nutrient issue, fish kills are a pretty good indicator that oxygen levels have dropped, and while they may not always be tied to a nutrient issue, it's one indicator that you might want to start digging into and doing some additional testing, right? Like if you had a landowner come to you and they said they had a fish kill, what would your next step be?
One of the first things I think I would look at would be the color of the water. Do I see evidence of an oxygen kill? When oxygen kills fish, oxygen kills plants too. And it's not uncommon after an oxygen-related kill, the water will turn a clear brown color where everything in it died. I would go back, I would look at the oxygen levels, although oxygen levels recover very quickly. I can't go out 2 days later and use an oxygen meter and see that there's been an oxygen depression, because they'll recover. But I might look at the nutrient levels. I might look at the history. Was there something in the watershed, or did the landowner do something in the recent history that could have contributed to it? Was there a heavy rain event that led to a pond turnover? You could certainly use the visual cues like you talked about, not only the dead fish, but the color of the water. I tell people when they're fertilizing, ideally you want to be able to see into the green water about 18 inches. More than 24 inches and it's probably too clear and you need to fertilize. Less than 12 inches and you need to stop fertilizing immediately and keep an eye on your pond, because if you can't see more than 12 inches in your pond, then that means there's so much phytoplankton out there that you're at a real risk of an oxygen problem. Visual cues like that, or visual cues like sudden changes in water color, all should be paid attention to. And I like the fact that you use that, because you don't need to be able to solve the problem as a landowner, but you may need to report it. If you're watching your local river and you suddenly see the river change colors or see some indicator that something's going on, report it. Give your local biologist a call and let them know, hey, I'm concerned about this. It doesn't look right. And a lot of times things just not looking right. I mentioned we started off talking about the risk of cyanobacteria, for example. And a lot of people tell me, well, I want to have my pond tested to make sure it's safe. I'm like, well, you can't. Cyanobacteria are always there, and the cyanotoxins only occur rarely, and when they do, they're temporary. So you might test it today and they're not there. They might be there tomorrow. The best thing you can do is look at the water. If the water looks gross, don't go swimming. Don't let your dog go swimming. If the water looks like it's got green and blue paint all over the surface and an oily sheen, I wouldn't get in that, and you shouldn't either.
Yeah, and a lot of that goes back so much to having a good awareness of landowner or water body placement in a watershed. So the area around the land one owns, that drains to a certain point. So we're all in a watershed. So as a landowner, you want to know where your placement is in a watershed, what the adjacent land uses are, And then, like you mentioned, keeping an eye on all of those visual cues, not just if there's a problem, but all the time. Because often, if you know that, yeah, late every summer I get a small algae bloom, it's not a big deal, nothing's ever died, and then it goes away, that could be a normal natural occurrence as nutrients come into the system and they're used up and the water quality remains still adequate for fish. But if that happens every year and then something changes and it's a different color, or it is more blue-green, or you notice something died, then you also just start to have more awareness of how your system's functioning and what's normal and what's abnormal. And smells can sometimes give us some indicators of that. Mm-hmm. And so just being visually aware, noticing smells, and you can do testing then if you really think there is an issue. And I think one major red flag, if you start to have that awareness, would be if there's an issue every year, because then you also have an indicator that somewhere the problem is reoccurring, whether it's within the property. It could be that someone has a pond and it is downstream of a pasture, and maybe the fix there is to move animals to a different pasture or put in some kind of vegetative buffer between where the animal use is and where a pond is. So there's lots of ways to just be aware, be creative, and solve problems when they're minor, and being a little bit proactive before it becomes a larger issue.
You're correct in that the location can be a real giveaway. For example, sometimes it's obvious. Maybe you have a pond that's downstream of a chicken farm, and the chicken farm, they'll scrape the litter out and pile it up, and then you have a big rainstorm and it all flows downstream. And sometimes it's a change in the landscape around the water body that you don't expect. You never know how it's going to impact the water body that you love and care about. So it's a good idea to be proactive, pay attention to what's going on around you, and when something does change, keep an eye on it.
Yeah, you brought up two really good points there. The federal government or state government can do all the water monitoring that they want. We can try to do, as University Extension, a good bit of water monitoring around the state. But we have so many water bodies, we can't even begin to come close to monitoring all of them. And that's a whole nother reason why citizen scientists and building all this local capacity is so important, because having folks to recognize these indicators on the landscape, if it's not reported, nobody literally knows that it's there or that it's happening. And so just having folks sharing and identifying and seeing these local issues helps us to resolve the problem early too, because otherwise nobody would know about it.
There's 4.5 million small bodies of water in the United States that are like ponds or small lakes. And the vast majority of those are privately owned. And I don't even want to venture a guess of how many hundreds of thousands of miles of small streams there are. The government agencies can't monitor all of that. It's really up to the people that use them to pay attention. They're the eyes on the ground. They're the ones that can see a problem in its early stages, and there's still something you can do about it. As long as it's reported and actions are taken, a lot of times we can fix these problems before they become too severe. One of the things I get a lot of calls for is people that want to get their water tested. And I try to explain to them a lot of times that there's 100,000 different things that can be tested for, and each one of them carry a cost. So it's not really feasible most of the time. When is it a good time to have your water tested?
Okay, that's a great question. And it's also kind of, I hate to say complex again, but it's a little bit complex. So you're right, testing can be advantageous sometimes. And I get a lot of calls like this too, right, where people do want their water tested. And it's all kinds of different water. So that's the first place to start is, what are you using the water for? Because we've gotten calls about pond water. I've gotten calls about water people recreate in or swim in. Some that have springs on their property that want it tested for bottling and drinking, all kinds of things, right? And each one of those activities requires a different water quality, if you will. And in fact, when we determine, and the federal government determines what quality of water we require, it's based on the designated use of that water. Is it for transportation? Is it for recreation? Is it for aquatic life, drinking water, shellfish harvesting, all these categories? So you first have to have a good understanding of what is the designated use of this water you have sampled that you want tested, right? Because that's going to give us some indication of how clean does it need to be and how do we define clean. Secondly, if it is, let's say, a spring water sample, you have to know that there are more than 80,000 man-made chemicals on the planet. And so we can measure a lot of different things in that water sample. And we're not going to measure them all. And we never do because it's way too expensive, right? And it's really unnecessary. And that goes back to the first part. What's the designated use? So if we're looking at a water body for fish, the place we're going to start is alkalinity, hardness, dissolved oxygen, pH, maybe nutrients.
Yeah, I think that alkalinity is the thing I test first most of the time, and nutrients are probably number 2 on the list.
Yeah, and I'll add to that, taking one water sample gives us a snapshot in time of a water body. So when we're doing routine monitoring or routine surveying of a water body, that is a systematic, routine assessment of the water quality trends over a fairly long period of time so that we get a sense of what the general water quality is. And that can even change if there's a big rain event, that, the water quality in a water body could be different after a storm event versus during a time of the year where the base flow is lower. So it's so important to consider when you're taking a sample and how much information are you going to get from a snapshot too. So those basic, physical and chemical parameters we just talked about, that's what we do in usually when you're training folks in pond management, we do that when we're training folks in basic chemistry at water stewards, because those are some of the most basic water quality parameters without even getting into a lot of other contaminants. Now, if it's a water body that you're recreating in, a thing I'd add to that is bacteria, because that's going to be something that's of a concern. So if folks are swimming and there's potential that folks have open cuts and sores, then you want to know if there's bacteria in the water. And so there's relatively simple methods we can train people on for that, or you could send it to a lab. And I think for that, it'd be more reasonable to send it to the Department of Health, because you're going to be looking for something like E. coli, which is an indicator bacteria for pathogens, bacteria that cause disease. And we just use E. coli because it's a good indicator. So that's another way you might test for something. And then really, if we're looking at a water body for watershed health, I would actually go to biomonitoring with macroinvertebrates, because they give you more than a snapshot. You're surveying a community of aquatic insects that can survive in the conditions of the water body. So by understanding who's there in the community and what different tolerance of pollution they have, you get a pretty good snapshot of the health of that water body over a longer period of time, because they're living a life cycle there and the communities that show up. And I find that sometimes to be the most exciting kind of monitoring, because you're getting more than just a snapshot in time.
All very good points. I agree with the coliform bacteria for water bodies that people swim in. I get calls. Actually, got a call just a couple of days ago from someone. Usually it's, we're having a youth camp in this location. We want to make sure the water is safe. And my response is usually, well, the water's never safe. The biggest risk is going to be drowning. But if you want to test for something, coliform bacteria is about the only thing you can test for unless you suspect something else. Unless you have a suspected chemical, there's almost no way to test for it without testing for, as you said, 80,000 man-made chemicals that would break the bank to try to test for. So if you suspect something, like if my neighbor had a warehouse full of glyphosate and I think he poured it in my pond, then you can test for glyphosate. But if you don't suspect something specifically, and from my experience, 99% of the times that fish die and it's May to November, it was oxygen. If it's December to April, it could be oxygen, it might be alkalinity and poor water chemistry. But either way, it probably wasn't somebody poisoning your fish.
Well, I'll add one note on the E. coli, because we would use that in a freshwater system, but in a saltwater system, and actually the Mississippi coast is where there is the most bacteria monitoring done by the state, because we use the beaches. They're using Enterococcus on the beaches, and that's just because it's more of a saline environment. And so I'll just preface that if you're in a coastal region, we're probably not going to use E. coli.
And along the same thread, another thing I get a lot of calls about are testing for biological issues, not only things like cyanotoxins that come from cyanobacteria, but people read the news, they see that the brain-eating amoeba killed somebody in Washington State, and suddenly they want to make sure their pond's safe. And the reality of it is these things that hurt people and hurt animals, things like the brain-eating amoeba, Pitheosis insidium, which is a fungal organism that can hurt animals, they generally are extremely rare. I think your risk of getting the brain-eating amoeba is 1/10 your risk of being struck by lightning while you're at your farm pond. So generally speaking, you can't really test for these things, and the risks are so incredibly low. Why would you want to? The chances are just almost infinitesimally small that you wouldn't be able to find them if it was there.
Yeah, and to that point, we're still, in terms of the scientific community, is still in a rapid stage of learning more about cyanobacteria and those type of blooms and what really the mechanisms are that cause blooms, and how to find indicators that identify them earlier on. Because, as you mentioned, that it's really hard to test for them because they're always present. So really what you have to test for is the toxin, which is a lot more difficult and requires molecular techniques than just testing for cyanobacteria. So the science is going to continue to evolve on that front as we learn more both about their ecology and how to identify them. So it's not even something that's really feasible for the average landowner to have tested.
I agree with you, Beth. One thing with the cyanotoxins and cyanobacteria, if you're not familiar with that term, this is what we used to call blue-green algae. It's not really an algae, but there are hundreds and hundreds of species that occur in your water bodies any given year, and they're capable of producing up to a dozen different toxins, but it's still a fairly rare event for them to actually do it. And a couple of things about that is, one is they produce the toxins, they maintain it within the algal cell, and they release it upon their death. So a lot of folks, when they see a cyanobacterial bloom, the first thing they want to do is, how do I treat it? Give me an algicide. Well, first of all, the bloom will probably go away on its own through natural processes. And second of all, if you do kill it and the cyanotoxins are present within the cell, then by killing it, you're going to lyse the cell. The cell is going to rupture open, and that toxin will enter the water all at once versus slowly as the bloom dies off. So treating it is not really a good idea to avoid risk unless you're willing to basically close off that system and stay away from it until you can verify that there is no risk remaining. Well, Beth, I really appreciate you coming and talking with us today. We've covered a lot of ground. I don't think we even scratched the surface on a lot of these things, but this is a field in and of itself. I'm definitely going to have you back in the future to talk about water chemistry and water quality. But for now, I really appreciate having you here, and thanks so much for talking with us.
Yes, thank you.
Fish University is hosted by Wes Neal, an employee of Mississippi State University Extension Service and a faculty member in the Department of Wildlife, Fisheries, and Aquaculture. This podcast is part of the Natural Resources University network of podcasts. Funding was provided by the Renewable Resources Extension Act. If you have questions or suggestions, please go to the Extension website at extension.mississippistate.edu. Click on Natural Resources and then select the Fisheries tab in the drop-down menu. Or you can email me at wes.neal@msstate.edu.